Hello everyone. Today I will explain my computer organization architecture class homework. First, I want to begin with the explanation of instructions. What first part says. Normally, in RM32, loops and conditional structures are implemented using branch instructions such as B, BEQ, BLE, and BGT. These instructions internally modify the program counter, its PC, to redirect execution to another address. However, in this assignment, branch instructions and labels are forbidden. Therefore, I implemented all control flow by explicitly computing target addresses and manually updating the PC register using movgt R5. To continue with algorithms to implement part. This part what asked from us. The objective of this program is to calculate the sum of all integers from m to n inclusive. In other words, I need to compute m plus 1, m plus 2, m plus 3 until n. For example, if m is 3, n is 6, then result should be 3 plus 4 plus 5 plus 6. So the program must keep adding numbers starting from m, increasing by 1 each time until it reaches n. The inputs are already given in registers, as you see. Register 0 contains the starting value m, register 1 contains the ending value n. The final result, the completed sum, must be stored in R2. So R2 will act as the accumulator register that stores the running total. Normally in RM, as I said, normally in RM assembly, loops and conditional decisions are implemented using branch instructions like B, BEQ, BLE, BGE, and etc. These instructions automatically change the program counter to jump to another location in the code. We would also normally label such as loop or exit to mark jump targets. However, in this assignment, branch instructions and labels are strictly forbidden. That means I cannot use any B or B count instructions. Also, I cannot use labels for implementing control flow. Instead, all control flow must be implemented by explicitly modifying the program counter using the instructions like move PCs and value. So instead of branching, I must compute the address I want to jump to, store that address in a register, manually update PC using move PC register. Also, this assignment requires specific registers to use for specific purposes. For example, R3 must store the bytes per word value. In RM32, each instruction is 4 bytes, so R3 is set to 4. R4 must store the calculated offset. This represents how far the program should jump. R5 must, if I'm not mistaken, R5 must store final computed target address. This is the address that will be loaded into the PC. R2 stores the running sum. Finally, when loop finishes, the program must terminate using SVG. Also, I want to add that the loop continues as long as m is less than or equal to n. Once m becomes greater than n, the program exits, I can say. Now I want to continue with my code, but first I want to show a simple logic map of my code. What we are doing in this code. This program calculates the sum of all integers from m to n, as I said, and it goes like m plus 1, m plus 2, m plus 3 until n. In the check body, the loop condition is implemented mainly in the check body. Here, as you see, we check if m is less or equal to n or not. If it's less or equal to n, so we go inside the body part and we increase sum by n, like we increase sum by the value of m, then we increase m by the value of 1, then we again go inside the check part and check if condition is paid or not, and if condition is not paid, what it means m is bigger than n, then program exits, so code stops. Now we can look the main code of us. Since I have already explained what's the difference of this homework, I mean we don't use labels or branch instructions, so I will not explain that part again. I want to code walkthrough. First we see these three parts. The text means this is code. The global entry and entry create the entry point so the program can start running. Actually, entry is label, but it's not used for the loop or decision. It's not actually a workflow, so it's just the starting place. So I thought I can use this, and then we have initialization part. I set R2 to 0 because R2 holds the sum. It said in our instruction, and I set R3 to 4 because ARM32 instruction is 4 bytes. And why multiply by 4 later? Actually, because jump address use bytes, not instruction count. So if I say jump 5 instruction forward, that equals jump 5 multiplied by 4 bytes forward. So that's why R3 stores 4 bytes to convert instructions. Then we have that part. In that part, here I compute a reference address called base and store it in R11. Why PC8? In ARM state, when you read PC, it doesn't give the exact current instruction address. It gives current address plus 8 because of CPU pipelining. I'm not sure if I split through or not. So PC8 gives the real address of this instruction. I use that as a stable anchor so I can calculate the addresses of other blocks without labels. And then we come that part, what we did in that part. Since I'm not allowed to use labels like check and body, I calculate their address using base. I store check address in R8 and I store body's address in R7. How do I know offsets 12 and 36 are correct? Because I count instruction from base. Every instruction is 4 bytes, so 12 bytes means 3 instructions after base, and 36 bytes means 9 instructions after base. In other words, I counted the exact position of the CMP instruction and the first body instruction in the final layout. If I had the assembler listing, I could verify these addresses exactly, but logically it comes from instruction counting times 4 bytes. Now we come to that part. This compares M in R0 and N in R1. This says CPU flex, so we can do conditional instructions next. Then we come to these two lines. This is if-else part, but without branches. If M is less than or equal to N, I set R0 to R4 to 0. If M is bigger than N, I set R4 to 5. How do I know 5 is correct? Because exit is located 5 instructions after the start of my body in my layout. So I use 5 as an instruction count offset, actually here. Now we come to that part. With this part, I convert the offset from instruction to bytes. And why multiply with 4? As you see, R3 is 4. Actually, I said it, but I need again explanation because each instruction is 4 bytes and memory addresses count bytes. So if I want to skip 5 instructions, that's 5 multiplied by 4 and equals to 20 bytes. Now I come to these two lines. With this line, I build the actual target address. R5 equals to body address plus offset bytes. If offset is 0, target is body. If offset is 20 bytes, target becomes exit. Then we move to this line. We use this line for jumping, and this is the core rule of the assignment. All control flow happens by updating PC manually, not by using branch instructions. So because this asked in instructions, I used this for jumping. Now we come here. First we look this line. In this line we make air2 equals to air2 plus air0. As you know, air0 holds the sum, and we add current m, which is air0, to air2, and we make air2 with this new sum, and then we add 1 to air0. As you know, air0 is m, and we increment it by value 1. So next time we add the next integer to air2. This is like the loop. And then with this part we repeat the loop. To repeat the loop, I jump back to check. I use the same pattern again. Put offset in air4, compute target in air5, jump using movpt air5. Since I won't exactly check, the offset is 0. And we come to exit cut. When n becomes greater than n, the check block chooses exit, and we reach SVG2, which terminates the program as required in the instruction. Thank you for your attention to my video. That's all for my homework.